Welcome to Lecture 4. In this lecture we begin our discussion of Unit 2, which is about Boolean Algebra, which is definitely one of the most important topics in this course. I would strongly suggest that you look through Unit 2 in the book and notice the large number of theorems that we have there that help us to understand how Boolean Algebra operates. You should familiarize yourselves with these theorems and understand how to apply them. Some of the main ones we will discuss now. By Boolean algebra, we mean the algebra of Boolean variables. And a Boolean variable is one that can assume only two values. And those two values are usually denoted by 0 and 1. So in Boolean algebra, we have two operations that can be applied. So, for instance, let's assume that x and y are Boolean variables. Then, as I mentioned, we have two operations. These two operations are OR, which is denoted by a plus sign, and which is denoted by a dot. And the two operations are defined in the following way. Let's look first at OR. Okay, the way that we read this is we have 0, ORed with 0 is 0. 0 ORed with 1 is 1. 1 ORed with 0 is 1. And 1 ORed with 1 is 1. So the one way we can say this a little more briefly is to say that 1 ORed with anything is 1. And furthermore, the only way that the OR of two Boolean variables will end up to be 0 is if both of the individual variables are also equal to 0. If either one is equal to 1, then the OR of those variables will be 1. So that's how the OR operation is defined. And then for the AND operation, 0 ANDed with 0 is 0, 0 ANDed with 1 is 0, 1 ANDed with 0 is 0, and 1 ANDed with 1 is 1. So the way to say this more briefly is to say that 0 ANDed with anything is 0, and if the result of ANDing two Boolean variables, or the only way that the result of ANDing two Boolean variables will yield a 1 is if both of those variables are 1. Another bit of terminology that we need is the word complement. When we have a Boolean variable x and then we put a prime after it, it denotes the complement of x. And the way that is defined is this. The complement of x is equal to 0 if x itself is equal to 1. And it's equal to 1 if x itself is equal to 0. So the complement is just the other. If x is 0, the next complement is 1. If x is 1, the next complement is 0. Now, having made this definition, we can make some observations. x ORed with x complement is always equal to 1. Now, that may not be obvious to you at first, but just think about it this way. If x is equal to 0, then x complement is equal to 1. And 0 ORed with 1 is 1. On the other hand, if x is 1, then we don't even have to worry about x complement, because 1 ORed with anything is 1. So it's clear, whatever x is, if x is just a binary variable and can only assume the values of 0 and 1, then it's clear that x ORed with x complement is equal to 1. Now, we can one thing we can do to make this even clearer is to develop what's called a truth table. And in this case, the truth table would look like this. A truth table is just an exhaustive listing of all the possibilities for a problem. So if x is a Boolean variable, then it can only have the two values at 0 and 1. And once we know the value of x, then everything else in the problem is determined, because if x is 0, then x complement must be 1. And 0 ORed with 1, x ORed with x complement is the same thing as 0 ORed with 1. And we can come up here to the OR table and see that 0 ORed with 1 is indeed 1. On the other hand, if x is equal to 1, then x complement is 0. But 1 ORed with 0 is also equal to 1. As we can see here, 1 ORed with 0 is 1. So the truth table simply verifies what we already said, that x ORed with x complement is equal to 1. Furthermore, x ANDed with x complement is always equal to 0. And we can, if that's not clear, we can make a truth table for this. By the way, when we write the AND of two Boolean variables, sometimes we simply write them together like this, x complement, and don't even put the dot in there. But for right now, I'll put the dot for you, just to remind you that this is the AND of those two Boolean variables. So again, the two possibilities, since x is a Boolean variable, it can have the value of 0 and 1, and once we know x, everything else in the problem is determined, because if x is equal to 0, x complement is 1, and 0 ANDed with 1 is 0. Remember, 0 ANDed with anything is 0. And if x is 1, then x complement is 0. And 1 ANDed with 0 is 0. And we can see those two results here from this AND table. Again, 0 ANDed with 1 is 0, and 1 ANDed with 0 is 0. One other thing I'd like to point out while we're looking at these tables is that notice that if we regard this right here as the main diagonal of the AND table, then the table is symmetric about that diagonal. And the same thing is true over here for the OR table. If we draw a main diagonal, this is symmetric about that main diagonal. Now what that means is simply that 0 ORed with 1 is the same as 1 ORed with 0, and 0 ANDed with 1 is the same as 1 ANDed with 0. This is these are referred to as the commutativity laws. OR is a commutative operation, and AND is a commutative operation. And that simply says that when you're ORing two, in fact it applies to any number of Boolean variables, if you're ORing Boolean variables together, the order does not matter. Similarly, if you're ANDing Boolean variables together, the order does not matter. So that's an introduction to a little bit of knowledge here about the AND operation, OR operation, and the complement. Now, what we've been talking about is discussed in your book on the pages up to and including page 39, and I believe most of those early theorems are pretty clear. They won't be too surprising to you. But as you move on to page 42, there are some theorems that might surprise you a little bit, so I'd like to discuss some of those in more detail. So we're moving on now to page 42. What your book refers to as simplification theorems. And the first one that we see is this, xy. Notice that that's the product of two Boolean variables, and the book has not put the dot in there. So xy or xy prime, or y prime or y complement, you'll see different people refer to the complement as in different ways, either as prime or complement. But anyway, xy or xy prime is equal to x. Now this might seem surprising to you, but the way that we can understand this is the following. So if we want to understand this a little bit better, we'll notice that xy or xy prime is the same thing as x ANDed with y or y prime. But as we said right here, if you take a Boolean variable and OR it with its complement, you always get 1. So y ORed with y prime is simply 1. And any Boolean variable ANDed with 1 is itself. So x ANDed with 1 is x, and so we do indeed get the expected result, x. Let's look at another example. The theorem, Theorem 213 says x or xy is equal to x. Now, how does this make sense? Well, one way we could derive this result is the following. X is the same thing as x ANDed with 1. In fact, we saw that in our previous example. X ANDed with 1 is x, and this is the same thing as saying x is equal to x ANDed with 1. So this x here we could rewrite as x ANDed with 1, and then we just bring down xy. But now that we've written this in that way, we notice that that is the same thing as x ANDed with 1 or y. But 1 ORed with anything, remember from our Boolean table above, 1 ORed with anything is 1, and 1 ANDed with any variable is the variable itself. And so, sure enough, we get the expected result of x. And now to move to Theorem 214 in your text. X or y prime ANDed with y is equal to xy. And this is not, as you'll see, I think this is not surprising, because if we multiply out the left-hand side, we get xy or y prime y. But as we noted right here, if we AND any Boolean variable with its complement, we always get 0. So coming back down here, y prime ANDed with y is 0. So this is xy ORed with 0. And any variable ORed with 0 is that variable itself. So sure enough, we get xy. So one message you should take away from this is that these theorems may be a little bit surprising, but after you look at them in some more detail, they make perfectly good sense. However, it's nice to be familiar with them. I mean, even if you don't know them, you'll end up coming to the correct answer, but it might take you a little bit longer. Knowing these theorems can help to save a good bit of time. Let's look at a few more examples. If we look at 212D, it says x or y ANDed with x or y prime is equal to x. Now let's see if we can understand this one. Okay, well, if you multiply this out on the left-hand side, you would get xx or xy prime or yx or y prime. And now we need to look at each one of those and see what we can do with it. Well, first of all, any Boolean, we're looking at the x term, any Boolean variable ANDed with itself is itself. 0 ANDed with 0 is 0. 1 ANDed with 1 is 1. So xx is simply the same as x. Now, I don't have any more to say about xy prime, so I'll just bring that down. And the next term, yx, well, we learned that the AND operation is commutative, so yx is the same thing as xy. So I'll bring that down as xy. And then finally, and we've already touched on this, y prime, that fits into the category of a Boolean variable ANDed with its complement. And as we said up here, any Boolean variable ANDed with its complement is always equal to 0. So this last term is 0. Okay? Now, there are various ways we could proceed, but what I'll do now is I will group together these two middle terms, the xy prime or xy. These two could be grouped together. This is not the only way we could simplify this. This is just one way. So when we group them together, we'll get that. And now we make the observation that any Boolean variable ORed with its complement is equal to 1. Now we realize that any Boolean variable ANDed with 1 is the Boolean variable itself. So the x1 term simply becomes x. Any Boolean variable ORed with itself, I'm looking now at x or x. So any Boolean variable ORed with itself is itself. That is, in other words, 0 ORed with 0 is 0, 1 ORed with 1 is 1. So x ORed with x is x, or, excuse me, x or 0. And as we have already said, anything ORed with 0 is itself. And so sure enough, we get x on the right hand side just as we expected. As I think you probably are already beginning to see, it is very important that you have these tables for OR and AND operations. You need to have those memorized. I don't expect you to memorize all these theorems, and I'm not sure that that would be a good use of your time, but it is definitely an excellent use of your time to memorize the tables for OR and AND to be thoroughly familiar with them, to to know, for instance, that 0 ORed with any variable is the variable itself, 1 ANDed with any variable is the variable itself, 1 ORed with any variable is 1, 0 ANDed with any variable is 0. Those kinds of things you just need to have right at the top of your head. Now, those are examples of some of the theorems that I think might seem a little bit less familiar to you. And then in this section, there are 2 more theorems that would be certainly unfamiliar to you and very, very important. And these are called De Morgan's Laws. These are on page 47, and the way they look is this. The way that I like to read this first line is to say that the complement of a sum is the product of the individual complements. And for the second line, the complement of a product is the sum of the individual complements. That is very important to remember, and as we will see, will be useful in some of the problems that we will attempt. In the problems at the end of this section, we're asked to simplify some expressions, so let's look at some examples of those. And by the way, just to remind you, these are De Morgan's Laws. So let's look now, for instance, at maybe problem 2.3, and maybe just as an example, let's look at B. We have A, B prime, or CD, and that sum is ANDed with B prime E or CD. Now in this problem, all these symbols A, B, C, D, and E, they're all assumed to be binary variables, and we're supposed to try to simplify this expression that we've written here. Well, my approach would be to go ahead and multiply all of this out. So we have, well, let's see. Maybe we should be a little more careful, because notice if you look at this, actually we might be able to make more progress. Rather than multiplying it out, we notice something. If I if I replace AB prime by X and CD by Y, and I replace B prime E by Z, and then CD once again is Y, I can make this shorter. Now in the end I'll need to put my answer back in terms of the original variables, but I think that by doing this I can make things a little shorter. So let's see what happens. So if I have X or Y ANDed with Z or Y, we would get XZ or XY or YZ or YY. Now, let's think about that for a moment. Well, I'm going to go ahead and write down XZ or XY or yz. I'm not sure I can do too much with those at the moment, but I know from what we've already talked about that yy is simply equal to y. Any Boolean variable ANDed with itself is itself. 0 ANDed with 0 is 0. 1 ANDed with 1 is 1. So yy is equal to y. Now, let's think about grouping these last three terms together. And we can do that in the following way. We have xy is the same thing as yx. And then yz I'll just bring down like this. And then we know that y can be written as y ANDed with 1. Now you might be wondering why I did that, but it's to set up what I'm going to do next, which is this. I'll factor out y out of those last three terms, and I have x or z or 1. And now bringing this over, I have xz or y ANDed with x or z or 1. But notice that it doesn't matter what x or z are, since I have that 1 there, and 1 ANDed with, 1 ORed with anything is 1, then the term in parentheses will be 1. And now I can finish this up. I'll bring down the xz, and anything ANDed with 1, any variable ANDed with 1 is the variable itself. So I just end up with xz or y. And now, as I said, now we have to put our final answer back in terms of the original variables. So x was a b prime, that's x. Z is b prime e, and then y is cd. So our answer is that, which actually can be simplified a little bit more. We can look at this b prime term. Any Boolean variable ANDed with itself is itself, and so our final answer would be a b prime e or cd. Now I know that that's probably might seem a little bit alien, but that's the way. That's one of the easiest ways to do this problem. Suppose you had not seen this simplification of letting ab prime equal x and cd equal y and b prime e equals z. Let's see how you would have proceeded in that case. So let's go back to the original problem. We have ab prime or cd, ab prime or cd, ANDed with b prime e or cd. And now I want to do the same problem, but this time I'm not going to do this business of substituting x and y and z. I'm just going to go ahead and do it directly and make sure we come up with the same answer. So, because this is probably more likely how you would have done it, since I assume most of you are doing this for the first time. So when we multiply everything out here, we'll get a b prime e, or a b prime c d, or c d b prime e, or c d c d. Now we notice in the first term the b prime, and again, any Boolean variable ANDed with itself is itself. So this is the same as a b prime e. We can't do much with the second term, so we'll just bring it down. A b prime c d. The next term, we can remember that we can write these things in any order we wish. And so I think it helps you to keep up with things if you write them in alphabetical order. So I'll rewrite the third term. I'm not going to do anything with it except to just rewrite the order of those variables. So we'll get B prime, C, D, E. And likewise, we can rewrite the order of the variables in the fourth term. Instead of C, D, C, D, we can get C, C, D, D. Now, proceeding, we'll have A, B prime, E again for the first term, and A, B prime, C, D for the second term, B prime, C, D, E for the third term, and then for the fourth one, well, any Boolean variable ANDed with itself is itself. In other words, 0 ANDed with 0 is 0, 1 ANDed with 1 is 1. So C ANDed with C is C, and D ANDed with D is D. And now we can, let's write, I think the way I would proceed now if I were you is I would switch the second and third terms. So I get A, B prime, E, or B prime, C, D, E, or A, B prime, C, D, or we can rewrite that last term, if you wish, as 1 ANDed with CD, because remember, 1 ANDed with any Boolean variable is a Boolean variable itself. And of course, if we do that, then the last two terms can be grouped together in this way. We'll factor out CD and get that. And of course, anything ORed with 1 is simply 1. So we get A, B prime, E, or B prime, C, D, E, or 1 ANDed with CD. And that is the same as A, B prime, E, plus B prime, C, D, E, plus CD. And we're still not done, because now we can say A, B prime, E, and we notice that there's a CD in that second term, so I'm going to reorder the second term like this: B prime, E, C, D, and I'll rewrite that last term as 1 ANDed with CD, and so we get A, B prime, E, ORed with B prime, E, or 1 ANDed with CD. And this is the same as A, B prime, E, ORed, and again, 1 ORed with anything is 1, so the term in parentheses is 1 ANDed with CD, and 1 ANDed with anything is that thing itself, so we get A, B prime, E, or C, D. And once we get to this point, I don't see any further simplification that can be done. And if we compare this result to what we had before, we see that it is indeed the same. It just took us a little bit longer to get to it. And of course, you might have done things differently. For instance, in the step where we switch the second and third terms, let's see if I can recall again where that is. Right here, and going from this step to this step, we switch the second and third terms. That wasn't really necessary. You might very well not have done that, and that's fine, because we saw that we could, as we saw down below, we can combine the B prime CDE plus CD terms at the end here of this line. In other words, we could have gone ahead and combined these two terms, but to do so, we would have needed to rewrite B prime CDE as B prime E CD, or rewrite it as CD B prime E. I mean, there's just a number of different things that you can do, and you shouldn't feel like you're locked into this. You just need to understand the basic principles. But the important thing to know then is that however you get to the answer, we see that the final answer, this and this, are indeed the same. So that's how you would do a problem similar to 2.3b, where you're asked to simplify some expression. And now I'd like to look at another example. Let's look at problem 2.5, where you're asked to, the direction to say, multiply out and simplify to obtain a sum of products. So let's go ahead, we can understand what multiply out means for sure, and simplify. Let's look at those two first, and then we'll talk about this terminology, sum of products. So let's look at A. First, we have A or B ended with C or B ended with D prime or B ended with A, C, D prime or E. Okay, so we want to, again, the directions tell us to multiply out, to simplify, and then to obtain a sum of products. So multiplying this out, we understand what that means. And by the way, after you've done these things a few times, you can probably skip some steps. Right now, I'll go through pretty much every step, but I'll try to point out places where we could make things faster. So I guess the first step that I would take would be to multiply the first term times the second term, and then also the third term by the fourth term, and then we'll multiply the resulting two terms. So when we multiply the first term times the second term, we get AC or AB or BC or BB. Now, if you have already begun to catch on to this, you might simplify this some. I mean, for instance, you know that BB is equal to B. And so that would be one thing you could simplify. But then you might also remember that once you've simplified BB to B, then B or BC is also B. And similarly then, so these two terms, the last two terms here, are B. And then B ORed with AB is also B. So all these last three terms just add up to make B. So the term in parentheses here, what I'm saying is that this term in parentheses is just equal to AC or B. But if you don't recognize that right away, and you probably don't right now, after all, you don't have that much experience with this, well, it's perfectly fine if you don't recognize it. Just go ahead and expand everything out as I have done. But if you do recognize it, then go ahead and take advantage of it, because that will help you to get to the end more quickly. Okay, so that's multiplying out in the first and second terms, and now we multiply out the third and fourth terms. So when and D prime with AC D prime, I'm going to go ahead and write that as AC D prime D prime, and you might very well know by now that the D prime at the end of that is just D prime. So if you want to write that as just AC D prime, that's fine. But I'm going to go ahead right now and write out everything. So we have AC D prime ORed with D prime E, ORed with AB C D prime, and then ORed with BE. So when we multiply out, we AND the third and fourth terms together, that's what we get. And now we go back and try to do some simplification. And again, I'm going to try to avoid doing too many steps at once. We'll try to take it easy, try to go step by step, but at the same time, do remember, if you see simplifications more quickly, by all means, use your insights. So we'll have AC or AB or BC, and then any Boolean variable ANDed with itself is itself, so we get B here. And likewise, we use the same principle in this second parenthetical expression, because D prime ANDed with D prime is in fact D prime. So the first term becomes AC D prime, then that's ORed with D prime E, or A B C D prime, or BE. And now what I would do is maybe rewrite this first term in the following way. Let's maybe we could write AB is the same as BA, or BC, and then B we could write as B ANDed with 1. Over here, what I'll do over here is I will bring down the first term and switch the order of the second and third term. So I'll get or A, B, C, D prime, or D prime E. That's just switching the second and third terms, and you'll see why we do that in just a moment. Or BE. Now going to the next line, this becomes AC, or factoring out of B now, we have B ANDed with A, or C, or 1. And now over here on the second term, notice that we can have A or AB. This is the reason that I switched the second and third terms. It was so that I could do this operation. I noticed that if I factor out the CD prime, we'll get that A or AB ANDed with CD prime, and then we'll be left with D prime E or BE. And now coming down, this is AC or B ANDed with, again, if we have any Boolean variables ORed with 1, we get 1. So A or C or 1 is 1. Now, the A or AB that you see in parentheses there, you might recognize that, but if you don't, that's okay. We can rewrite this as in the following way. A can be rewritten as A1, A ANDed and with 1, or AB, C, D prime, or D prime, E, or BE. And now just continuing, AC, or anything ended with 1 is itself, so B ended with 1 is B. And now we see that this term in parentheses here could be rewritten as A ended with 1 or B, then C D prime, or D prime E, or BE. Continuing, AC or B. Here we have A. 1 ORed with anything is 1. And so we can write 1. And then C, D prime. Or D prime E. Or BE. And 1 ended with anything is that Boolean variable itself. So we can just drop the 1 and say A, C, D prime, or D prime E, or BE. And I believe that that's about as much as we can simplify both of these terms, and now we're finally ready to multiply these out. So indeed this is a tedious problem, but it gives you practice with this algebra. So try to be patient. We won't do many problems that are this tedious, but it is good practice. So now multiplying this out, we have AC D prime, or AC D prime E, or ACBE, or BACD prime, or BD prime E, or BBE. Now, remembering that we can write these variables in any order, I'm going to rewrite the variables in the first one as AACCD prime. I'll leave the second term as it is, ACD prime E. The second term I'm going to write simply in alphabetical order, A, B, C, E. For the next term, also in alphabetical order, A, B, C, D prime. The next one, B, D prime E, no change there. And for the last one, remember any Boolean variable ended with itself is itself, so BB is the same thing as BE. Now, going to the next step, AA is A, CC is C, so we have AC D prime, ORed with AC D prime E, and ORed with AB CE, or AB CD prime, or B D prime E, or BE. Now we have certainly multiplied things out. We have simplified to some extent, and actually we now have this sum of products form that the book requested. Now understand what that means is that each one of these is a simple, each one of these terms here in this line is a simple product of Boolean variables, and we have all these summed up together. So this is a sum of products. So actually we've solved all the requirements of this problem. We've multiplied it out, we have simplified to some extent, and we've written our final answer in sum of products form. However, we've not simplified this as much as possible. Now, you may or may not recognize that, and the good news is that in the near future we're going to learn a systematic way to determine whether or not an expression is simplified as much as possible. But for right now, let's just investigate this and see if we can try to find out, just through observation, how we might simplify a little bit more. So you might have noticed that the first two terms both have ACD prime. So we could take ACD prime out and rewrite those two terms as ACD prime ANDed with 1 or E. And we know that 1 ORed with E will be 1, and so that's going to lead to some simplification there. Now, how might we simplify the remaining terms? Well, we could write the first term as BE AC, and then we could interchange the next two terms, B D prime E. In fact, rather than saying interchange the next two terms, let's just say that we'll move this A, B, C, D prime term all the way to the end. So we have BD prime E, or BE, or A, B, C, D prime. Now, once again, let's review what happened there. These first two terms, I just took ACD prime out of both of them, and then was left with 1 or E. I changed the order on this term, but kept it where it was. Now I have BEAC. I took the ABCD term to the end, and then bring down BD prime E and BE. Now, you'll see why we did that in just a moment. So again, now to simplify this, 1 ORed with anything is 1. And then so this term in parentheses is 1, and anything ANDed with 1 is itself. So this is just ACD prime. Now, notice that the next terms could be written as BE ANDed with AC, or D prime, or 1. And then the last term is simply A, B, C, D prime. Well, this is a familiar story. 1 ORed with anything is 1, so this term here in parentheses is 1, and 1 ANDed with BE is BE. So we have A, C, D prime, or BE, or A, B, C, D prime. And finally, I believe if we take take the BE to the end, we get A, C, D prime. Can be written as ACD prime ANDed with 1. The last term could be written as A, C, D prime ANDed with B, and then we bring BE to the end. And now these two terms, we have A, C, D prime ANDed with 1 or B, and of course, once again, 1 ORed with anything is 1, and then the resulting 1 ANDed with anything is that thing itself. So we have A, C, D prime, or B, E. And finally, now we can simplify this no further. So this is our final result And once again, as I mentioned before, don't despair if that was not, if you don't feel that you could have reached that point, don't worry too much, because we will be learning a systematic way to simplify expressions in the very near future. But this gives you a lot of practice on simplifying and multiplying out. And again, this final expression is called a sum of products because each one of these two terms is a simple product of Boolean variables, and then of course we've summed up those two products, so this is a sum of products form. And so that concludes this problem.